The standard enthalpy of formation. The standard enthalpy of formation, delta H super zero sub F, super zero meaning standard conditions, is the heat change that results when 1 mole of a compound is formed from its elements at a pressure of 1 atmosphere. The standard enthalpy of formation of any element in its most stable form is 0. Look at these. Oxygen, the heat of formation is 0, but ozone, the heat of formation is 142 kilojoules per mole. For graphite, the stable form of carbon, the heat of formation is 0, but the heat of formation of diamond is 1.90 kilojoules per mole. Here's a table of standard enthalpies of formation. There's a more extensive table in the appendix at the end of your textbook. The standard enthalpy of reaction is the enthalpy of reaction carried out at 1 atmosphere. For the hypothetical reaction, A moles of A plus B moles of B yields C moles of C plus D moles of D, we can write that the heat of reaction is equal to C times the heat of formation of compound C plus D times the heat of formation of compound D minus A times the heat of formation of compound A plus B times the heat of formation of compound B. This can be summarized as the heat of reaction equals the sum of the heat of formation of the products minus the heat of formation of the reactants. Hess's law states that when reactants are converted to products, the change in enthalpy is the same whether the reaction takes place in one step or in a series of steps. Enthalpy is a state function. Here's an example. Benzene, C6H6, burns in air to produce carbon dioxide and liquid water. How much heat is released per mole of benzene combusted? The standard enthalpy of formation of benzene is given, 49.04 kilojoules per mole. Here is the balance reaction. 2 moles of benzene plus 15 moles of oxygen yield 12 moles of carbon dioxide plus 6 moles of water. We can substitute in for the heat of reaction equation 12 moles times the heat of formation of CO2 plus 6 moles times the heat of formation of water minus 2 times the heat of formation of benzene. Notice there's no term for oxygen since the heat of formation of oxygen is 0. Substituting in the values from the table, we arrive at a negative 6535 kilojoules. That's the heat of reaction for the entire combustion of 2 moles of benzene. To calculate the heat released per mole of benzene, we must divide the 6535 kilojoules by 2, yielding a negative 3,268 kilojoules per mole of benzene. Here's a Hess's law problem. We can calculate the standard enthalpy of formation of carbon disulfide, CS2, given these 3 reactions. Carbon graphite plus oxygen yields CO2. Sulfur plus oxygen yields sulfur dioxide, and carbon disulfide plus oxygen yields carbon dioxide and sulfur dioxide. Notice we are given the heats of reaction for these 3 reactions. Write the enthalpy of formation of carbon disulfide. We do that by starting with carbon graphite reacts with 2 moles of sulfur to form carbon disulfide, CS2. Add the given reaction so that the result is the desired reaction. If we take graphite plus oxygen, yielding CO2, if we take sulfur plus oxygen, yielding 2 moles of SO2, since we're doubling everything, we have to double the heat of reaction. And finally, we reverse the last reaction. CO2 plus 2 SO2 yields CS2 plus 3 O2, and this then is now a positive 1,072 kilojoules per mole. If we add all of these reactions, we get the reaction that we want, and we do the same thing to the heats of reaction as we did to the equations. The heat of reaction then is 86.3 kilojoules per mole. The enthalpy of solution, delta sub solution, delta H sub solution, is the heat generated or absorbed when a certain amount of solute dissolves in a certain amount of solvent. Delta H of solution equals delta H of solution minus delta H of components. H of solution minus H of components. Here is a table of heats of solution of some ionic compounds.